Okay, year 12, so let's do a retrieval roulette before we start today's lesson. So pause, answer these in your book, and then come back and then you can mark them. For question 8, just draw the direction of the current whatever way you want. Okay, right, so here's your answers. Pause, mark those. I'll talk a wee bit about the answer for 8 once you get the rest of those marked, so mark the rest of them and then come back. So for 8, remember for that one, you use your right hand and you put your fingers round the coil in the direction that the current is going. So whether that's this way, and then your thumb points to the north pole of the magnet, or you might have it where it's coming out of the page at you that way, and then the north would be at the other side. Okay, the rest of those I hope are obvious enough. Right, let's get on to today's stuff. Right, I want to start by going over these questions that we were doing last day. I've looked at a few of them. I was looking at them sort of as they were coming in on Friday. So if yours was a wee bit later on coming in, I probably haven't actually had a chance to look at it yet, but I still will, don't worry. In general though, from the ones that I have seen, we are doing really well. I'm very impressed because this motor effect, I think, is one of the hardest things in the whole topic. So if we're getting it, brilliant. There's also one thing in one of the questions, the way it's drawn has confused a few people, because then you've got the same style of question right in the next one. Anyway, page 220, mark and correct these as we're going over them. Okay, so we had to fill in words here. In the motor there are two magnetic fields. The field due to the north-south of the permanent magnet and the field due to the electromagnet. So I put in there the coil, a couple of people put in there the current. I would mark that correct as well. Okay, so it's the force between these two fields that makes the coil turn. The current is applied to the coil through two contacts called brushes, and these touch the split ring or commutator. If there was no commutator, the coil would just make a half turn and then stop. The commutator makes sure that the push on the coil is always in the same direction. I think I said to a couple of people that came onto the meet to ask for help like this, the brushes and the commutator, generally in exams they wouldn't really ask you for that information, but it's helpful to know the words around. Okay, please excuse my lazy answers here, but two ways of reversing the direction of rotation. You could reverse the magnet, or you could reverse the way the current is flowing, and by doing that you would just flip the battery the other way around. And then for this one here, what happens to the power of the motor if the current is increased? Well, the power is going to increase. Again, sorry about my laziness. Large number of turns, the power is going to increase. An iron core is used, power will increase, and a stronger permanent magnet is used, the power will increase. They're all going to increase the power. Right, page 221 then. So question 1, 3 ways in which the strength of an electromagnet may be increased. So you can increase the current flowing, insert an iron coil, or increase the number of coils of wire that you have. B, an electromagnet can be switched on and off. Suggest one situation where this would be an advantage over a constant field permanent magnet. So like moving cars in a scrapyard, go around, turn your magnet on, pick up a car, take it wherever it needs to go to, turn off your magnet and it'll drop it. Yeah, that's the big example there. Now this here's the one that I was talking about that a few people got wrong, right? And I think it's maybe this arrow or the funny angle that this is drawn at, because then you got a very similar question correct like on the next page. So let's have a wee look at this. The motor effect can be demonstrated using the apparatus shown in this diagram. When a current is passed through the movable brass rod, it rolls along the fixed brass rails. For a start, this looks a bit random compared to what we have been talking about, but you've got your magnet, you've got just two wee rails, and then this is a rod that is sitting loose, right? So it's going to move in the direction of the force that you get using your Fleming's left hand rule. Okay, so for part A, state the direction of the magnetic lines of force between the poles of the magnet, so north to south. B, this was the one that a few people got wrong. I was going to say a bunch of people, but not a bunch of people, but enough that it made me think, oh no, we don't understand this, but then I was always reassured by that next question. So to figure out this, if you think of this as like, see this wee arrow here, as if that's pointing out of the page that helps me. I'm going to try and keep my hand down here. So I think sometimes up here it can get a wee bit confusing direction wise. So current, we put our second finger in the direction of the current, and remember it's always conventional current. So you can see here I've marked on my wee arrow, and that's actually what that arrow is there. That's showing you the direction of the current. I've no idea why they put that on. First finger goes in the direction of the magnetic field, so north to south. Oh, so if I'm putting my first finger in the direction of the magnetic field, my second finger in, this is really awkward, let me move my camera. Okay, I think that's maybe a little bit better there. So first finger in the direction of the magnetic field, now my camera's in the way, so pointing down the way. Second finger in the direction of the current, which is coming out of the page towards me. So with my hand, with the three things perpendicular to each other, my thumb is pointing to the right. So this thing is going to roll off to the right. And I think it's the funny, like, direction, don't know if that's the right word, perspective that diagram is drawn at, which is what has confused a few people there. Okay, so Fleming's left hand rule, first finger in the direction of the magnetic field, north to south, second finger in the direction of the current coming out of the page, and then your thumb's pointing to the right, so this will move off to the right. So Lazy Patterson strikes again, arrow to the right. Well, I really should have written it moves to the right. The rod is placed back in its original position. What will happen to the rod if the poles of the magnet are reversed? Well, then it's just going to do the opposite. So it's going to roll off to the left, or if you wrote it, it'll move the opposite direction. Perfect. Now for part D, the rod is placed back in its original position. What will happen to the rod if the poles of the battery are reversed? So I sort of think, depending on what way you thought about this, either answer would be correct. So if the magnet was still reversed, then it's going to go back to the right again. But if the magnet was back to the original and everything else was back to the original, then it's going to go to the left. So it depends how you read that question, okay? But it's just going to do the opposite of what it was doing before. Okay, question 3. Below is a simplified diagram of a DC motor. The loop of wire is horizontal and it's in a horizontal magnetic field. So remember, our magnetic field is going to go from north to south. DC means direct current. I couldn't remember if we talked about that yet. It's actually what we're going on to look at the rest of this lesson. Which direction is the force on side AB of the wire loop? So that's this side here. So again, Fleming's left hand rule. Put your first finger in the direction of the magnetic field, north to south. Second finger in the direction of the current. So this one's going into the page. So now my thumb's pointing down the way. So this side's going to go down. And then CD, if I do the same, put my first finger in the direction of the magnetic field, north to south. Second finger in the direction of the current. This time it's coming out of the page towards me. So that's where I'm doing that. And my thumb's pointing up the way. Shouldn't have said north. Thumb's pointing up. So that's going to go up the way. This here, bit dodgy. Explain how these forces cause the loop to rotate. Oh, I can't remember who it was now. Somebody give a lovely answer for this. I've told you if it was you. I just said they create a turning effect, which is clockwise, because this is going down that way and that's going up that way. So they create a wee overall clockwise turning effect, or a moment, I suppose. And what can you say about the force on side BC of the loop? A few people left this blank actually, because it's parallel to the magnetic field. If you remember back to that very first lesson where we were talking about this, the force is always maximum whenever your current is perpendicular to the magnetic field. So that's like here and here, but there's zero force whenever it's parallel to. So this here, there'd be no force on that bit. Okay. So if you turn over to 223 for me, I just want us to make sure today that we know the difference between direct current and alternating current. Direct current literally just means the current is going in the same direction the whole time. So conventional current, always going from positive to negative, that would be direct current. Now, the size of the current can change, like the current can increase and decrease, but as long as it's still going in the same direction, then it's direct current, okay? Alternating current, this is what the electricity that we have in our houses is like. It changes direction many times per second, so like it's going just back and forth, back and forth. Our mains electricity supply is a frequency of 50 hertz. Do you remember in waves we learned about frequency? The number of waves that pass per second. In this case, it just means that the current is changing direction 50 times per second. Okay, so the current, like the electrons, are just going backwards and forwards and backwards and forwards. So we need to draw in a few wee graphs for this. So let's get that done. Right, so I'm going to draw 3 for this one. So get your wee axes drawn, pause, whatever, get this done. So if you have just a steady current flowing, if we're plotting, I should have said actually, we're plotting current against time, and all of these, it could I suppose be voltage against time. Say it's just a constant supply, then as time goes on, the value of the current just stays the same. Say it's increasing over time, doesn't have to be starting from 0, so let's say like that. Then because it's always above the x-axis, then it's always going to be direct current. Even though the magnitude of it is changing, it's still direct current. It's still always in the same direction. Let's say it was changing up and down and up and down and up and down. I'm just going to go wild here, and I'm going to do in the negative. So like that. Because it hasn't gone across that axis, it hasn't changed direction. So these are all direct current. You can probably guess what I'm going to make sure I show in this alternating current graphs. These alternating current graphs, I should say. So make sure you get those down, and then let's do the alternating ones. Okay, let's do 3 again. So let's say, what will I do? Let's say we had a current of a certain value, and then after a while it just changed direction, and then it changed direction again, etc. Then we would end up with that. So it's this, it's the crossing over of the x-axis really that shows whether it's alternating. Could be like this. Could be, let's go like that. Okay. Don't know how realistic any of these actually are, but yeah, as long as it's crossing the x-axis, because remember, I probably should have done arrows on all my axes here, but the values above the x-axis are 0, or not 0, the values above the x-axis are positive, and the values underneath are negative, and the negative is just going to refer to the direction. So if it's crossing over that x-axis, it's alternating, which means it's changing direction. Okay, I need you to have a wee go at those questions on page 224 and 225, and there's room on the pages, you can just answer them on them. Okay, bye.